Alright everyone, hello. Today we are going to do some more inductor and capacitor problems. This is part 2. We have a little bit more tricky problems today, but we're going to get through them, and let's go. So we have to find the voltage and the current, and then we're going to plot them. The first thing I'm going to do is find the voltage, okay? I think that's easiest. To find the voltage, we are going to have to apply our transient analysis, which is step 1, from negative infinity to 0. And we're going to go ahead and draw that circuit. So let's look at this. At negative infinity, right, we are open, okay? So this whole portion right here is disconnected because we are at point A, okay? So it's just going to look like this. And as you can see, nothing is attached to this that could charge anything or whatever, just an empty capacitor, right? We're going to expect that this is empty because it's discharged everything to the load during this phase. And we'll just go ahead for formality's sake and just call it an open circuit, okay? So we know that the voltage across this is just 0, okay? And likewise, because it's a capacitor, we know that it's also 0. We have voltage continuity. We know that there's no current because it's an open circuit, but we do not know the current at 0 plus right after the switch because current continuity is not guaranteed. So we're going to go ahead and move on to step 2 of our transient analysis, 0 to infinity. And this time, the entirety of the circuit is alive. So we're trying to find voltage. The simplest way to do this is just a nodal analysis. So at node 1, we have V minus 5 over 2K. I'm going to go ahead and put the times 10 to the 3 plus V over 4E3 plus, and we've got our 10 microfarads right here. I believe it said microfarads. Yes, microfarads. And that's just going to be 10E negative 6 V prime equals 0. Let's go ahead and divide everything by 10 to the 10e negative 6, and we are going to get 50 V minus 5 plus 25 V plus V prime equals 0. And then combining this all, we've got V prime plus 75V minus 250 equals 0. V prime plus 75V equals 250. And now we can solve the differential equation, step 3. And we have a forcing function that's a constant, so we're going to have a particular solution. Let's go ahead and find the homogeneous solution first, where V prime plus 75V is equal to 0. So that's just simply K1, we'll call it K1, e to the negative 75t. And for V particular, we're going to guess that it's K2. We're going to go ahead and plug it back into this equation, plug each V into this equation. We're going to find that the derivative of a constant is 0 plus 75 K2 is equal to 250. And dividing both sides by 75, we are going to get 10/3. And so our V of t is going to be 10 over 3 plus K2 e to the negative 75t. Now we're not yet finished. We're almost finished. We still need to find K2. Thankfully, we know what V of 0 plus is. Our initial condition is just 0. And so we will have 0 equals 10 to the 3 plus K2 And then e to the 0 is just 1, so I'm not going to write it down. K2 is equal to negative 10 thirds. And so v of t is equal to 10 thirds plus, minus 10 thirds e to the negative 75t. Now let's go ahead and graph this so that we can get it out of the way. So we know that our voltage, starts at 0 because of our initial condition right here. So we're going to start at 0 right here. And let me go ahead and bring this equation up so that we can analyze it. This is just some classic algebra 2 stuff. We've got our v of t right here, and the time on the time axis, so v of t right here. Now, think about what happens as this goes to infinity, as t approaches infinity. Well, this is a negative sign, so really it's a 1 over e to the 75t. So as we're going to infinity, this is going to approach 0, and so what's left is just a 10 thirds. So we are going to have an asymptote that is approaching that is approaching 10 thirds. Okay? That's the graph. Let's go ahead and find I of t. Now, we are going to go ahead and just apply a loop analysis rather than a nodal analysis, which is what we did here. So I'm going to go ahead and copy the infinity portion, 0 to infinity portion of the transient circuit analysis. And we'll call it step 1 because we've already found the initial conditions. We're going to go ahead and apply a loop analysis. And notice that we're going to have 2 loops here. And one of them is going to be called I1, and one of them is going to be called I2. It doesn't matter which one we call which. We just need to make sure, that we're consistent. I'm going to call this one I1, and I'm going to call this one I2. We're going to go ahead and draw the loops. Loop 2, minus 5 plus 2e3 I2, right? Because we're going to go through loop 2 first. And I'm just doing loop 2 first because it's arbitrary. Plus 4e3 I2. And notice that I1 is going to be canceling out, or it will be opposing I2, not necessarily canceling out. Minus I1 equals 0. Let's go ahead and simplify this. Let's go ahead and write loop 1. Loop 1 is going to be this 4e3 with I1 going up, I2 going down in respects to our loop 1, plus, and because it's a capacitor, we are going to have this integral from 0 to t with I1 on the inside, okay, not I, but I1 d sigma plus, and I'm just going to write this on the other side because on the next line because I'm running out of room, v sigma equals 0. Now, what is probably the best way to do this? The thing that I can immediately see, and this is where your intuition comes in and basic math skills. We have this integral, and we can't just put this in a system of equations, okay? Like on your calculator or something like that. I mean, you can try, but I don't think that you can do that. We only have one I2 here. So I think the best thing to do is to solve for I2 and get it in terms of I1. So let's go ahead and do that. 6e3i2 is equal to 5 plus 4e3i1. Divide both sides by 6e3, and we're going to get 5 plus 4e3i1 over 6e3. And we can just simply put this in here like so. And we will get 4e3 I1 minus 5 plus 4e3 I1 over 6e3 plus our little integral here, like so. And I'm running out of room. Like that. Let's go ahead and simplify this down. And we get 8e3i1 minus 20 plus 6 over 10 to the e negative 6 times the integral. Okay? And we're going to go ahead and continue this on the next page. And we are going to go ahead and plug in 0 plus so that we can get our I1 0 plus. Okay? Because we want to find the I of t right here, and the I of t right there is I1. Okay? So we need to find the initial condition going through I1. And this is just going to be 0 plus v of 0 plus equals 0. Remember, our initial condition for v of 0 plus is just 0. And so we get I1 0 plus is equal to 20 over 8e3, which is also equal to 2.5 milliamps. Okay? Finally, I believe that is this is step 2. Finally, we can take the derivative and solve. So derivative of 20 is 0. We're going to take the derivative of that integral, which is just the integrand. We're going to go ahead and divide both sides by 8e3. And wonderfully, we get 75. I1 is equal to 0. And we get I1 of t is equal to K1 75 e to the negative 75 t. Let's go ahead and solve for this initial condition. So I of 0 plus, for this constant right here, I of 0 plus we found was 2.5 e negative 3 is equal to K1. Boom, that's it. So I1 of t, which is also equal to I of t because that's what we're looking for, is equal to 2.5 e negative 3 e to the negative 75t. Man, that was a good amount of work for this problem. There is still a little more. We can actually check this with a nodal analysis that we had earlier. We can check for I of t, using the nodal analysis. So we're going to check with nodal. So you could have completely bypassed all of this loop analysis, because a lot of the times a loop analysis is pretty annoying because you want to find a current, and sometimes you're going to get these two currents, right? And it's annoying. You're going to have to do a lot of algebraic manipulation. So why not instead utilize KCL? Okay, KCL in the nodal analysis. So if we go ahead and get our our circuit at the infinity portion, we know that our KCL is looking like this, right? And we want to find this one right here. Well, guess what? If we call these two I1 and I2, I1 plus I2 plus I equals 0, we can find I if we just take the negative of I1 plus I2. And we actually know what I1 and I2 is from the voltage, right? We know that I1 is equal to V minus 5 over 2E3, and we know that I2 is equal to V over 4E3, okay? And we actually know what V is. We calculated it right here. And so if we plug in this V into this equation right here, then we should theoretically get the same I. So I is going to equal negative, and we're going to go ahead and plug, actually, to make this even simpler, we're going to go ahead and just have everything in terms of V, and then plug in at the end, right? We're going to multiply both sides by 4E3, and we're going to get negative 2V plus 10 plus V equals negative 3V plus 10. And when we plug it in, negative 3, 10, 3 minus 10, 3, e negative 75, t minus 10. Oh, oops. This is supposed to be minus right here. 4e negative 3i, 4e negative 3i, 4e negative 3i. And so we've got right here 10e negative 75 t, 4e negative 3i, and so I of t is equal to 2.5 e negative 3 e negative 75t. And there we go. We successfully checked our answer. Let's go ahead and do the next one. Alright, here's problem 2. It looks like we're switching between a 16 volt battery and an 8 volt battery for this capacitor right here. So step 1, as always, we're going to go ahead and find voltage first. So step 1, as always, the negative infinity portion. And we're going to draw out that circuit. I'm going to go ahead and put the A position right here. And in the A position, we are using the 16 volt battery. We have an open capacitor because of the long transient phase, the negative infinity, long DC environment. We've got 10 ohms right here. Let's go ahead and look for the initial conditions. The initial condition starts with, for voltage, starts with 16 volts. And I1, I0 minus is just going to be 0. I0 plus is going to be question mark. Step 2, 0 to infinity. I'm going to go ahead and draw this circuit. The 16 volts is out of the picture now, and we've got our B right here because we're in position B. Our capacitor is active now. We've got 40 millifarads, and we've got this 10 ohm resistor right here, I believe. And we want to find the voltage first. So I'm going to go ahead and set up for a nodal analysis. Okay. So in our nodal analysis at this node, we're going to have V minus 8 over 10 plus V prime, or 10e negative 3 V prime equals 0. Once we solve this all out, we're going to get v prime plus 2.5 v minus 20. Actually, let me go ahead and just write all of that out. So we're going to multiply both sides by 10, and we're going to get 0.4 v prime plus v minus 8 equals 0. Divide both sides by 0.4, v prime plus 2.5 v minus 20 equals 0. Step 3 is to solve this differential equation. So first we're going to find our v homogeneous, which is just, we've got k1 e to the negative 2.5t right here, and then we've got vp is equaling to k2, because we have to have our guess because we have our little constant forcing function. We're going to plug that in. 0 plus 2.5 k2 is equal to 20, and so we get that k2 is equal to 8. So our full voltage is defined by 8 plus k2 e to the negative 2.5t, and our initial condition was 16 volts. That's what this original battery was charging this capacitor with. So we've got a 16 volt kick equals 8 plus k2. K2 is just equal to 8, and so v of t is equal to 8 plus 8 e to the negative 2.5t. Boom. Easy. So for this one, don't let that second battery, confuse you or scare you. It's literally the same thing. Okay? So all you're doing is stepping down into the battery. So what's going on here is that this capacitor ends up charging this battery, which is kind of interesting. And then once this capacitor gets depleted, this battery starts charging this capacitor. That's why we have, if you draw this graph right here, we're going to see that it stays at a constant 8 volts, right? It starts at 16, right? It starts at the 16 volts. It didn't ask us to draw the graph, but I think it's a good idea to draw anyway, even if you're not asked, so that you can look at this intuitively. It starts at 16 volts, right? But it doesn't go all the way down to 0. It actually just tapers off. It has an asymptotic behavior at 8 volts, because then all that is left is that 8 volt battery, and that capacitor becomes an open circuit because the impedance is so high, or impedance is such a, the impedance is just the resistance, the ohms, okay? The ohms right here become infinite. The capacitor doesn't accept any more charge, and so the voltage difference just stays at the voltage difference of this quote-unquote infinite power source. Let's go ahead and solve for I of t. We're going to solve for I of t in the exact same way as last time. We're going to solve it with a loop analysis, and then we are going to solve it using a trick with the nodal analysis like last time. Literally the same thing, guys. So we're going to have I1 here, but remember, this is now a battery, and this was charged with a voltage difference of plus minus and plus minus, okay? So we're going to need our plus minus for our capacitor. And so we're going to go ahead and just kick it off with the infinity portion, the positive infinity portion. Draw a loop 1. We've got negative 8, 10, and plus this integral. So negative 8 plus 10i plus 1 over 40e negative 3, 0 t I sigma d sigma plus v sigma equals 0. Let's go ahead and plug in 0 plus so that we can get our initial condition for the current. So it's just negative 8 plus 10I 0 plus, and then plus V0 plus. And remember what V0 plus was. V0 plus was just 16 volts, and we're going in through the positive side. Then we would get a positive 16. Now, if our battery were actually the opposite, and instead it was like this, and we're trying to find the current going down, then we would put a negative sign because it's being forced with a negative voltage, okay? So this is just 16 equals 0. And so we're going to get 10I 0 plus is equal to negative 8. I of 0 plus is equal to negative 0.8 amps. Step 2 is differentiate. We now have all the components to actually solve for this differential equation. What I'm going to go ahead and do is, we're going to go ahead and differentiate 10I prime plus 1 over 40e negative 3. That whole integral just becomes I is equal to 0. We're going to divide both sides by 10, and thankfully we're going to get 2.5i is equal to 0, and that's just a homogeneous differential equation, so we can easily apply k1 e to the negative 2.5t, and since there is no other constant here, we can just simply say that the k1 is I of t equal to negative 0.8 e to the negative 2.5t. Okay, and that should be the answer. We can obviously check with a nodal analysis, and the way that we check with a nodal analysis is we think about this. We have our I1, and we have our I1 here, but in our nodal analysis you'll see that our I1 is actually going into this node and then out of this node, right? So what we're going to say is that because we've defined this I1 as going into this node, we're going to say that the I that we found is automatically negative I, and the reverse, the V minus, right, because we've got this I going this way, and we want to find the branch of this because it's just the same, because it's just two nodes. That's why we've applied the negative sign. It'll just be V minus 8 over 10 because we've already accounted for our physical interpretation. Let's go ahead and solve for V. So we're going to get 8 minus 10I is equal to V. When we plug in that I, right, so technically I'm just checking to see if the voltage is correct, because if the voltage is correct, then that means our current is also correct. And we can see that it actually fits very nicely. Multiply both sides by 10 and negative, so V of t is equal to 8 plus 8e to the negative 2.5t. And that's it for this one. Alright, the last one. Now guys, this one I will admit is reasonably more difficult than the other two. And so bear with me, I am going to solve it in the exact same way as the other two. However, we are going to go ahead and solve everything with a nodal analysis first. Then we are going to apply a loop analysis, and you will see why this is the case. So first of all, it's going to start off really, really normal. We are going to have our negative infinity stage. All right. So let's go ahead and find our initial conditions. our initial condition right here for V0 minus is 2 volts, right? And the reason why it is 2 volts is because we've got this 2 volt branch right here. And remember, the initial conditions are based on where we want to find this V, since we're directly connected to a 2 volt battery when this inductor right here has been short circuited because it's in a DC environment for a very long time. We will have a voltage difference of just 2 volts, right? And so our V0 minus is 2 volts. Now, because it's an inductor, we cannot guarantee voltage continuity. And now we're going to have to think a little bit about our current right here. Okay, so we're going to notice that we've got a 2 amps going in to the node this way, and then we've got 2 unknowns, right? Two unknown voltages right here. But we actually know what this voltage is. We actually know what this current right here is because we can apply an Ohm's law saying V minus 0 over 2 is equal to this I right here. So we're going to call this I, that I, maybe I1, we'll call it I1, and we'll call this one I2. And so the KCL is going to look like -2 plus I1 plus I2 is equal to 0. And we know what V is because we have that initial condition right there. And so we will have -2 plus 1, because 2 over 2 is just 1, plus I2 is equal to 0. And so I2 is effectively 1 amp. And so we have down this branch right here, and we're trying to find the current, we're trying to analyze the current down this branch right here. Not this branch, not this branch, but this branch right here, okay? So we are going to use this 1 amp right here. And by current continuity, we can say that 0 minus is 1, I of 0 minus is 1, I of 0 plus is 1 as well. So in this circuit, the negative infinity portion is actually a little more involved. So keep that in mind. Step 2 is the infinity portion, the positive infinity portion. We're going to go ahead and draw the circuit again. Thankfully, that current source is gone. However, we have a problem. We have this guy right here. Now, let's go ahead and draw this nodal analysis first, and we'll see what happens. V minus 6 over 1 plus V over 2 plus, now what in the heck, 1/4 over 1/4, and then we've got our nice integral. But what do we do here? Well, what I've found as very helpful is applying an Ohm's law here. See, we're really pulling out everything out of our bag here. So we're going to have to identify with an Ohm's law the voltage of the inductor, okay? Because to find the V that we want, our big V right here, or our little v really, we're going to have to add, that V is equal to the voltage difference of this inductor plus the voltage difference of this battery. So we're going to have VL, V sub L, plus 2. Now remember, this integral is only applicable to the inductor. And so therefore, that V of sigma, that we've been doing the entire time, is actually VL of sigma, okay? It's not, it just so happened that during our times, V equaled VL of sigma. I mean, V of L, V sub L. But now V sub L has a 2. And so we need to find what V sub L is. And V sub L is just going to be V minus 2. And so we are going to get right here V minus 2, okay, or V sigma minus 2, V sigma, okay, plus I sigma is equal to 0. So this battery is forcing a voltage into this inductor right when we get out of steady state, okay? Steady state being when this inductor is just a short circuit, okay? Now we can go ahead and plug in 0 plus so that we can find V of 0 plus. And what was I of 0 plus at the time? I of 0 plus was 1 amp. 1 amp. Multiply both sides by 2. And I'm going to go ahead and combine these. This is negative 5, so it's negative 10. Plus V of 0 plus is equal to 0. And so we get V of 0 plus is equal to 10 thirds volts. And so we can remove this right here to being 10 thirds volts, and we know that. We know that permanently, okay? So we're going to get V prime plus 1/4 and then it's just going to be the integrand. So we're actually going to include that V minus 2 plus V prime over 2 equals 0. Multiply by both sides by 4. Divide both sides by 6. Minus 1/3 is like that. And so we're going to get our V homogeneous as being K1 e to the negative 1/6t, and V particular is equal to K2. We're going to go ahead and plug in K2, 1/6 K2 equals 3, 1/3, sorry, and K2 is equal to 2. We're going to plug this guy in. V of t is equal to 2 plus K1 e to the negative 1/6t. And then we're going to apply our initial condition. Our initial condition was 10 thirds. It's equal to 2 plus K1 e to the 0, which is K1 equals 10 over 3 minus 6 over 3 is just going to be 4 thirds. And so our V of t is equal to 2 plus 4 thirds e to the negative 1/6 t. And that's the voltage. I'm not going to solve the current, at least for this portion, with a loop analysis. Instead, I'm going to continue with the nodal analysis. Okay, so B I of t, solve with nodal analysis this time, and I will show you why. I'll show you why after we solve for this I of t. Okay, remember what we're solving for. We're solving for the I of t in this branch. Okay, keep that in mind. So let's go ahead and apply some KCL. We've got our KCL going out this way, and then we've got our KCL going out this way, and we've got our KCL going out this way. Okay, sorry for this one, because I was like, why do we have this too? Anyway, so we have our KCL going out this way, this way, and this way. Easy. So we're going to say we've got I1 right here, V minus 6 over 1, plus, let's call this the IL, okay? The I inductor. I inductor plus V minus 0 over 2 equals 0. And we're going to go ahead and just simply solve for IL. We're going to get 2V minus 12 over 2 plus V over 2 plus IL is equal to 0. 3V, we're going to get IL is equal to negative 3V minus 12 over 2. We're going to go ahead and apply that subtraction across, 12 minus 3V over 2, and then IL is equal to 6 minus 3 halves, and we're going to plug in the V that we found here. This guy cancels out, this guy cancels out, so we're left with IL is equal to 6 minus 3 minus 2e negative 1 6t. And we've got IL is equal to 3 minus 2e to the negative 1 6t. And you may be thinking, like, Alex, like, that's nice, like, solve it with nodal analysis, but I kind of want to do it the way that we've normally been doing it. And I'm going to say we are going to do it the way that we normally do it. Now, the problem is it will be a little more difficult and a little more involved, but we're going to go ahead and do it. All right, so we're going to solve V I of t, this time with a loop analysis. So we're going to have our nice circuit, and we're going to go ahead and make some loops. So the first loop we're going to say is L1. The second loop we're going to say is L2. Let's go ahead and apply our loop analysis. So we've got negative 6 plus I1 plus, now here is the funny part. We've got our inductor right here. We've got our 2 volts right here. That's not the funny part. The funny part is this inductor portion. Because what do we have in this inductor? We don't just have one current. We have 2. So I would actually use the DDT version right here, because it gets confused, like I prime, and it's kind of weird, and times 4. Okay, I like to see what's going on in here first. So I1 minus I2, and that is having a derivative applied to it, plus 2 is equal to 0. Okay, now if we simplify that out, we get 4I1 prime minus 4I2 prime plus 2 equals 0. And we are going to end up with 2 simultaneous differential equations. So let's go ahead and write this right here. Minus 2 plus 2I2 plus 4 ddt I2 minus I1 is equal to 0. Minus 2 plus 2I2 plus 4I2 prime minus 4I1 prime. And you're going to be like, what? What do I do here? Well, actually, from here, it kind of makes sense. Notice, look at these. They cancel out if we add them up together. So let's go ahead and do that. So I1 prime and I1 prime die. These guys die. And so what we're left with is I1 plus 2I2 minus 6. And this is actually really good because we're going to have I1 is equal to 6 minus 2I2. And look at that. We can actually eliminate one of the parameters so that we can do our single variable calculus, right? This is very similar to the one that we just did, where we had 2 loops and we needed to eliminate a variable, okay? So we're going to go ahead and find one of these equations that we want to eliminate. We already have it in terms of I1. So let's go ahead and eliminate all the I1s. Yeah, let's go ahead and eliminate all the I1s. Now, think about if we plug it into this equation. If we put in I2 into this equation, I1 in terms of I2, that's all fine, but what are you going to do with this one? I1 prime. You're going to do nothing. You're just going to be sitting there and scratching your head. So instead, what we're going to do is plug it into this guy right here. Plug it into this guy right here. And this is why I write it in DDT. Oh my goodness. DDT, right? Because you want to cancel out the variables before you've differentiated them, okay? So let's go ahead and take this one right here. Let's go ahead and plug in our I1 into here. And so we're going to get negative 2 plus 2I2 plus 4 d dt I2 minus 6 minus 2I2 equals 0. All of this guy simplifies down to 3I2 minus 6. Doesn't matter what this 6 is because it dies in the derivative right here. Minus 2 plus 2I2 plus 12, because this 3 goes out, basic calculus. I2 prime is equal to 0. I2 prime, divide everything by 2, 12, plus 1/6 I2 minus 1/6 equals 0. And you can see here, you are happy. You are jumping up and down seeing this 1/6 right here, because that 1/6 corresponds to our 1/6 that we found down here. And remember, we're just checking ourselves. We want to find this equation right here. Now, let's go ahead and solve this out. We've got step 2, I'll say. Step 2. Solve. So we've got I homogeneous is equal to 1/6 e to the, k1 e to the negative 1/6 t, and IP is equal to k2. We're going to differentiate both sides. We're going to get I2 is equal to 1/6 times 1/6, so it's just 1. Okay, I2 is just 1, and we get I2t equals 1 plus k1 e to the negative 1/6 t. Now here is the part that gets very, very extremely confusing, at least to me. Look at this. This is I2 of t. We want to find this, right? Not I2 of t right here. This is I2 of t. We want to find I of L, right? And so we need a voltage, we need an initial condition that is applicable to I2 of t, right? We know that the initial condition for the current down this way is 1, but we don't know what the initial condition is for I2. Yes, we have 0 minus 1, and we have 1 right here, but remember, this is just for that branch only. We never found the initial condition in this branch right here, and it doesn't have an inductor, so there's no law saying that it has to be 1 amp. Okay? So you're probably thinking, what are we going to do? We don't have an I2 0 plus, right? Well, don't fear. We have a V0 plus 10 over 3. So we have an initial condition by which we can find it in terms of. And because, and this is the beautiful thing about voltage, voltage is the same across. Okay? And how can we define an initial condition, right? A current, when we have a resistance and a voltage? Ohm's law, V over R. And so we're going to get 10/3 over 2. Okay, so our initial condition that we're going to be using here is actually 5 over 3 amps. Mind-blowing, isn't it? And now we have I2 of t is equal to 1 plus k1 e to the negative 1/6 t. But we're going to go ahead and call this 0, 10 to the 3, or 5 over 3 times 0. And we're going to get k1 is equal to 2/3. And then we've got I2t equals 1 plus 2, 3, e to the negative 1/6 t. But it's not celebration time yet. Like I said before, this is I2 of t. And so, after that entire wild goose chase, and stuff like that, you are still going to be forced to use a KCL. Okay? Because we've defined I1 going in this way, IL going out this way, and I2 going this way. And so our KCL is still going to be negative I1 plus I2 plus IL equals 0. We're going to go ahead and say that we've got the I2, right? And we've got the I1 actually, because we have I1 defined here, right? We have a dependency that we can use. And so we are going to say that we have negative 6 minus 2I2 plus I2 plus IL is equal to 0. We're going to get 3I2 minus 6 plus IL is equal to 0. IL is equal to 6 minus 3I2. And after our long, wild goose chase, we have 1 plus 2 over 3 e to the negative 1/6 t. Multiply across, and we get IL is equal to 3 minus 2e to the negative 1/6 t. And just like that, we get the same answer as before. Now, do you see why sometimes it's better to just use a nodal analysis? Right here, we solved for I of t in just a few steps just by using V. But here we've extensively proven it with this loop analysis. We expanded the differential equation and we got two differential equations, but we were able to thankfully cancel them out using a bunch of dependencies that we had to think about using what we know about circuit theory, okay? And then we had to realize what we were actually solving for, I2. But we don't want I2. We wanted IL. And so we had to get the initial condition for I2. And then in the end, we still had to use KCL because we had that node. How are we going to find IL? We had the dependency, and we found what I2 was. And we've got IL right here. So you would only use this method really if you wanted to find this right here. If you wanted to find I2, or alternatively, you wanted to find I1 right here. Okay? So yeah, if you prefer doing it this way, that's fine. The only problem is it's more intuitive. Definitely. It's definitely way more intuitive, like to choose a loop analysis so that you can use that loop analysis so that you can find it via straight up a current, right? And it's an inductor, so bonus points for it being a derivative rather than an integral. But sometimes you've just got to suck it up and use the alternative version. That's why I've been showing you guys how to do these problems with both the nodal and the loop analysis so that you can gain this intuition. I did not have this intuition when I was taking this class. Like this kind of problem, I made this one up, but there was one similar to that in my class, and this messed me up. But now that I'm able to look at this and analyze it, because I feel like I have a better grasp of nodal and loop analysis, I'm able to play on all of these, and even using Ohm's law in random places like this, right? This is just Ohm's law, just to find the initial condition right here, because the initial condition is literally just a constant circuit, like one of the ones that we did in Unit 1, okay? So that's it. This is advanced topics for the practice problems. I believe I'm going to have one more part. I'm going to have a part 3 of this to do just a little more fancy ones, but this is by far one of the hardest examples that I've had to do. So rest assured, if this is easy for you, good job. If not, please watch this video again. Please check out the last 2 videos if you did not understand this, because I go over a lot more simple circuits in the last 2 videos. Alright, I'll see you in the next one.